Howdy, my name is Ximena Barrutia. I study at Smith College. I'm part of the REU chemistry program at Texas A&M, and I'm working in Dr. Wooley's lab. Water is life. There's nothing more essential on Earth than water. We need it, our farm stocks and crops need it, and we depend on them. Without water, there will be no life on Earth. Only 3% of the water on Earth is fresh. Of the fresh water, less than 1% is located in swamps, rivers, and lakes. This means that 1% of the water on the Earth's surface is usable by humans. This shows that the distribution of water on the Earth's surface is extremely uneven. Additionally, the effects of global warming due to the human-generated greenhouse gases are impacting drinking water supplies, food, sanitation, and energy production. There are people that are struggling every day to access the quantity and quality of water that they need. This global crisis is happening everywhere around the world, including in the US. In places where agriculture predominates, water is being pulled out from the ground and sucked almost dry, leaving the earth collapse. This process is called subsidence and is caused by the exploitation of groundwater. This map shows aquifers in the United States. Each dot represents known areas of land subsidence, most prominently in California and Nevada, but also in the coastal regions of Texas and Louisiana. This global water crisis has caught the attention of many people, including scientists, who have been developing new strategies for water purification. One of these inventions is hydrogel technology. Hydrogel are networks of polymeric change known for their high water absorbency. They have been used as potential absorbents for removal of water contaminants, such as heavy metal ions and dyes. They work by absorbing polluted water and filtering out unwanted compounds. Then they will dissolve back and go back to their original state. There has been recent studies on a new hydrogel with better defined pores, capable of absorbing greater amounts of liquid while maintaining a better mechanical strength. This new type of porous polymeric material is called polyhypes. For the preparation of polyhypes, we use a technique called high internal phase emulsion. In the first step, we mix the organic phase and the aqueous phase to create a stable emulsion. At least 75% of the emulsion must be internal phase.
In my case, my internal phase is a toluene oil solution, which is added dropwise into the aqueous phase. This type of emulsion is known as an oil-in-water emulsion. This is actually a technique used to prepare mayonnaise, ketchup, and salad dressings. Here, the aqueous phase contains deionized water, surfactant, and monomer. Surfactants are a type of emulsifier that helps create a stable mixture. In cooking recipes, they use egg yolks and gelatin. In our case, we use molecules containing both a water-loving side and a water-hating side to help create a liaison between the two liquids. Here we can compare two flasks, A and B. Flask A doesn't contain any surfactants, while B does. We can observe that the emulsion in flask A breaks, while the one in flask B doesn't.
After the creation of the stable emulsion, the reaction continues by going through polymerization and purification. At Texas A&M, I'm working in Dr. Wooley's lab on this new porous polymeric material for water uptake. Her research lab is based on renewable and degradable polymers for biomedical and material applications to limit the adverse environmental impacts on these materials long term. My project's goal is to synthesize this degradable polymer from glucose and incorporate it into the high internal phase emulsion to create a porous polymer for the purpose of water uptake and pollutant sequestering. We hope for these porous polymeric materials to behave as superabsorbent and tough hydrogels while also being recyclable to tackle these global water resource challenges.